Section 11.3 Area of Polar Curves. Areas enclosed by polar curves. We would like to be able to use numerical integration to find areas enclosed by polar curves, just as we did with curves defined by the rectangular coordinates. Converting the equations to rectangular coordinates is not a reasonable option for most polar curves. So we would like to have a formula involving small changes in theta rather than small changes in x. While a small change delta x produces a thin rectangular strip of area, a small change delta theta produces a thin circular sector of area. Recall from geometry that the area of a sector of a circle is 1/2 r squared theta, where r is the radius and theta is the central angle measured in radians. If we replace theta by the differential d theta, we get the area differential dA equals 1/2 r squared d theta, which is exactly the quantity that we need to integrate to get an area in polar coordinates. Now here's a diagram that shows the Riemann sum with the area of a rectangle, and if we add up a bunch of rectangles, we get the total area. Well, here we're going to add up a bunch of sectors of a circle to get the entire area. Integrating sine squared and cosine squared. Here we have the double angle formula for cosine, and that's equal to cosine squared minus sine squared. Well, we can't integrate sine squared directly, and we can't integrate cosine squared directly. So we have cosine 2 theta equals, well, it's a double angle formula. And then we replace cosine squared with 1 minus sine squared. That's 2 sine squared. Minus 1 and divide by negative 2. Sine squared is 1/2 minus 1/2 cosine 2 theta. Well, instead of integrating sine squared, we can integrate its equivalent. And we can do the same thing for cosine squared. So cosine squared is equal to 1/2 cosine 2 theta plus 1/2. Find the area bounded by the graph of r equals 2 plus 2 sine theta. So here we have the cardioid. And we're going to sweep a magic windshield wiper around this shape. And we say it's magic because we're sweeping this windshield wiper and it can change lengths. So we're sweeping all the way around the shape. Well, in order to sweep all the way around the shape, we have to go from 0 to 2 pi. And here's the 1/2 r squared theta. Well, we square 2 plus 2 sine theta. And we replace sine squared with 1/2 minus 1/2 cosine 2 theta because we can't integrate sine squared, but we can integrate its equivalent. Then we distribute the 4 through. 4 plus 2 is 6. And then we can finally integrate. And we're going from 0 to 2 pi. When we plug in the values, we end up with a value of 6 pi. Find the area of one petal of r equals 2 sine 3 theta. Well, the petal starts at 0, and then we would have to sweep through until we get back to 0. And we get back to 0 at pi over 3 for this particular rows. And here's the 1/2 r squared d theta, where r is 2 sine 3 theta. Well, we have to square both the 2 and sine, so we get 4 sine squared. We replace sine squared with 1/2 minus 1/2 cosine of 6 theta now. Normally that would be 2 theta, but we already had a 3 theta here, so 3 times 2 gives us the 6. Distribute the 4 through, we get 2's, and then finally we can integrate. We're integrating from 0 to 3, and when we plug the values in, we get a value of pi over 3. Find the area of one petal of r equals 4 cosine 2 theta. Well, here's a rose with 4 petals, and we want the area of one petal. Well, we could integrate from negative pi over 4 to pi over 4, but instead of doing that, let's integrate from 0. Let's start at 0 and sweep through to pi over 4 and just double that. So we have 2 times 1/2 r squared d theta, where r is 4 cosine 2 theta. Well, we square the 4 and get 16. We square the cosine and get cosine squared. But we can't integrate cosine squared. We have to replace that with its equivalent, which is 1/2 cosine now of 4 theta plus 1/2. We can distribute the 16 through, and we get the 8's. And then finally we can integrate, and we'll get 2 sine 4 theta plus 8 theta. We're integrating from 0 to pi over 4. So when we plug the values in, we get an answer of 2 pi. Find the area inside the circle and outside the convex limacon. So here we have the circle, and down below we have the limacon. Now when we sweep this magic windshield wiper around, we want all of the windshield wiper, all of it to the circle, but then minus the limacon right here, leaving the area in between. Well, we want to find the two intersection points. So we set the two equations equal to each other. We add the sign over, divide by 4, and we find that sine is 1/2 at pi over 6 and 5 pi over 6. So here's your pi over 6. Here's the 5 pi over 6. And again, we want all of the windshield wiper to the circle, but then minus out this little piece to be inside the circle, yet outside the limacon. Here's the math for that. We have 1/2 r squared from pi over 6 to 5 pi over 6. This is all of the circle and minusing out the area of the limacon. So let's square both. That gives us 9 sine squared. And when we squared 2 minus sine theta, we get 4 minus 4 sine theta plus sine squared theta. And we combine this into one integral. We factored the 1/2 out and combined into 1. Well, we have 9 sine squared minus sine squared. That's 8 sine squared. And then we have the plus 4 sine and the minus 4. We replace sine squared with its equivalent so that we can actually integrate this. Distribute the 8 through and we get the 4s. Now 4 minus 4 is 0, so we're left with these two in between here. And then we can finally integrate. Negative 4 cosine 2 theta is negative 2 sine 2 theta, and 4 sine is minus 4 cosine. And we're integrating from pi over 6 to 5 pi over 6. When we plug the values in and do a little arithmetic, we get 3 square root of 3. Find the area of the common interior of r equals 3 cosine theta, and r equals 1 plus cosine theta. So here we have the cardioid, the 1 plus cosine, and we have the circle on kind of the right side. So we want the common interior, which is kind of this oval shape right here in the middle. So we want the area from 0 to the intersection point, and that follows the cardioid. And then it switches off, and we want to find the area from the intersection point to pi over 2 of the circle. So we're going from 0 to intersection of cardioid, and then intersection to pi over 2 of the circle. We want to know where these two intersect, so we set them equal to each other. Minus the cosine over, divide by 2, and cosine is 1/2 at pi over 3. So we can go from 0 to pi over 3 on the cardioid, and then pi over 3 to pi over 2 on the circle, but that would only be half of the area, and then we can just double that area that we find. So here's doubling 1/2 from 0 to pi over 3 of the cardioid, and then plus from pi over 3 to pi over 2 of the circle, and we have the 1/2 r squared. So if we distribute the 2 through to both of these, the 1/2s are going to be gone. Now 1 plus cosine theta squared is going to be that right there, and then we have the 9 cosine squared. We have to replace both of the cosine squareds with its equivalent so we can actually integrate. 1/2 plus 1 is 3/2, so there we have the 3/2 theta. We have the 2 sine theta, and here we have 1/4 sine of 2 theta. And over here we multiply 9 through and have the 9/2. We have 9/4 sine of 2 theta plus 9/2 theta. And we're integrating from 0 to pi over 3 on the first one, and 0 to pi over 3 to pi over 2 on the second one. Then when we plug in the values, we do lots of arithmetic, we end up with 5 pi over 4.